Hello and welcome to RATA Skillathon 2026. This is the season 2 of Skillathon. The intention of the Skillathon is to create high quality training content online, which is easily accessible to the entire industry, especially our engineers, to learn online and to improve their skill sets. Today we have a very interesting topic, which is on the cold room heat load calculations. And we are very fortunate that we have Mr. Parthiban from Danfoss, India, who is joining us today from Bangalore to do this entire training session. Mr. Parthiban, thank you so much for taking time out to do this session for us.
Thank you, sir. Thank you for having me here. Good afternoon. My name is Parthiban. So, I am from Danfoss Application Engineering team. So, I have experience of 15 years in this refrigeration and air conditioning industry. So, today, as sir told, I'm going to present about heat load calculations for cold rooms. If
Awesome.
we talk about
Please go ahead. You can go ahead with the entire session. And
yes,
yeah, over to you, please.
yes, okay. So, we will discuss about heat load calculations for cold rooms today. So, if you see, heat load, like there are a number of heat sources which will contribute to the heat load for cold rooms. So the heat sources can be classified into three broader divisions. First is transmission load, second is product load, and then internal load. So these three heat sources will generate most of the heat, so which will be like removed by our refrigeration equipment to maintain the product at a particular temperature or a lower temperature compared to our ambient. So this is how the cold storage uh, will work. So we will discuss about this all the heat sources, like how to calculate the heat load because of these heat sources in detail in the coming slides. I'll start with transmission load. So I'll explain what is transmission load. Transmission load is the heat transmitted from outside atmosphere to the cold storage because of conduction or convection or radiation. So these three sources. If you take a cold storage, so in this screen if you see, like there is a cold storage which is maintained at plus 4 degrees Celsius, whereas outside the cold storage, like in the ambient region, so the temperature is higher than 4 degrees Celsius. Here in this case, if you see, so in the like left and right side, like across the walls it is 35 degrees Celsius, on the roof it is 45, on the ground level it is 25. All the temperatures are high compared to 4 degrees Celsius which we are maintaining inside the cold storage. So there will be four walls. Across the four walls, 35 degrees Celsius is there. On the roof, it is 45. On the floor level, it is 25. Because of this temperature difference, from 35 to 4, there is a difference of 31 degrees Celsius. So there will be heat gradient. So because of this heat gradient, so the heat will transfer from outside atmosphere to cold storage. So we will be using a puff panel or some insulation material to prevent the heat from entering the cold storage. Even though we use a puff panel or a insulation material, it cannot avoid 100% heat transfer. There will be some heat transfer. How much heat transfer is happening, so that will decide how much heat load we are going to remove. So we have to calculate how much heat is entering. So to calculate that, we have different formulas which we will discuss. I'll split it into two. So heat entering the room because of the four walls, and heat entering the room because of floor and ceiling. So we can split it into two. So first, let us discuss about heat entering because of the four walls. So let us say like we have a wall in north, south, east, and west. So we have to calculate the heat load, heat entering the cold storage through these four walls. Each and every wall has to be separately calculated. The first formula to calculate this transmission load is Q equal to UA delta T. So Q is the heat load which is entering because of transmission. U is the heat transfer coefficient of the wall material. If you are using a polyurethane foam or like rock wool panel, so each and every material will have a U factor, which we call it as a heat transfer coefficient. Then A is the area of the wall through which the heat is entering. If you're calculating for north wall, it will be the area of north wall. If you're calculating for the south wall, it will be the area of south wall. Then delta T is the temperature difference between outside and inside. If you see this picture, the difference between 35 and 4, which is 31, 31 will be the delta T. So this is very simple formula. But here, if you see, calculating area is easy. So we will have a puff panel, which is like almost rectangle or square. Calculating the area will be very easy. So each and every side wall, like say north side wall will have some area, south side wall will have some area, east wall or west wall will have some area. The area calculation is very easy. Then second, delta T calculation also very easy. So we need two temperatures. One is the outside ambient temperature, and second is what is the temperature we are going to maintain inside the cold storage. So these two are already available. So what we are going to maintain inside the cold storage will be decided by the product. If you are storing vegetables, it will be 4 degrees Celsius. If you are storing meat, it will be minus 20. Each and every product will have different temperature RH. So those details are available in a history handbook, which we can refer. So this is very easy to calculate. So inside temperature is known, outside temperature is known. So delta T calculation is very easy. Then area calculation also very easy. So if you talk about U factor is the heat transfer coefficient. So we have a formula to calculate the heat transfer coefficient. So let us discuss that in detail. So like if you see the formula, you can see it's a very big formula. It looks complicated. I'll explain it in detail. So you can see the picture. If you can see my cursor, there is a picture on the right side. So here you can see x1, x2, and x3. So I'll explain what is x1, x2, x3. So this is a puff panel. So in this puff panel, you will have a material puff which can be like with some thickness, maybe 100 mm or 50 mm, 150 mm. So the thickness of the puff is x2. X1 and X3 are the sheet metal which is on the both the sides of the puff funnel. If you take a puff funnel, there will be two sheet metals. Between the sheet metals, puff will be there. So X1 is the thickness of sheet metal which is on the outer side, and X2 is the puff thickness, and X3 is the thickness of sheet metal on the inner side. So these three are the thicknesses. The next, you can see K1, K2, K3. So what is K1, K2, K3? So these three we call it as conductive heat transfer coefficients. So what is conductive heat transfer coefficient? So heat transfer within a solid material is called conductive heat transfer coefficient. So the sheet metal or puff or and again sheet metal, all three are solid. So because of which there will be heat conduction from outer sheet to puff, then puff to inner sheet and inner sheet to the room. So these conductive heat transfer coefficients are like K1, K2, K3. It varies with material. So for like SS, it will be different. For like different metals, it will be different. For different insulation materials, it will be different. We will get this data from the suppliers of these materials. Then you can see two more data, which is HI and HO. HI and HO is the convective heat transfer coefficient. So convective heat transfer coefficient refers to the heat transfer between a fluid and solid. So fluid can be a liquid or gas. Solid should be solid. So if you see the outer surface, the sheet metal of the puff panel will come in contact with the atmospheric air. Air is a fluid. The sheet metal is a solid. There will be heat transfer between air and the sheet metal. This we call it as convective heat transfer. So there is a coefficient depending on the fluid type and the material. Each and everything will have. If it is water and sheet metal, will have different coefficient. Air and sheet metal will have different coefficient. So sheet metal can be any material. Material wise also it will change. So based on this HI and HO will be calculated. These data are also available in the internet or like in history and books, with which we can calculate the U factor. The U factor formula is mentioned here. You can see, but you can feel like this is so complicated. Do we have to do this U factor calculation each and every time we do a cold storage design? It's not required. The reason is many of the insulation materials which we use in the industry are already the U factor of those materials has been already calculated. If a supplier is launching a new insulation material, he will calculate this U factor and he will establish that in their catalog, so or somewhere. So these U values are readily available. But if you are going to design a new insulation material, then this has to be done actually. So that's why I wanted to explain this in detail. But if you go like in the next slide, I'll explain. So if you see this slide, this is the table where the U factor values of different insulation with different thickness is tabulated. If you're using a polyurethane foam, so where like the thickness is 50 mm, then U value is 0.46. The thickness is 150 mm, which is 0.15. If you keep on increasing the thickness of the material, then the U value will reduce. So that means, so you like increasing thickness will reduce the heat conduction. So because of the reduction in heat conduction, like your heat load will reduce. So that is what it's mentioned here. The data of polyurethane and rock wool and polystyrene, these three materials are available here. If you have some new insulation material, you can get the data from the insulation supplier. So U value also is available. So let me go to next slide. Okay. So we have the U value, we can calculate the area, and then we can do the delta T calculation. So, but in addition to actual delta T, there is one more thing we need to do in the delta T, which is a correction factor. Why a correction factor is required? So, if you take the ambient temperature and the inside temperature, and if you calculate the delta T, it will work up to some extent for a normal cold storage. In cases where the solar radiation is directly falling on the wall of the cold storage, the wall of the cold storage is exposed to the solar radiations, then the delta T will be little bit higher. So to calculate that correction factor, there is a table here. So this correction factor has to be added to the delta T value, which we have already calculated. So if your wall is south facing and you can see light surface color gray and dark surface color, the paint or like the coating what you use to the wall surface, that also will decide the heat load. If it is light surface, it will emit back the radiations. So because of which your delta T is only 2 degrees Celsius. If you are going to gray or dark, the delta T will increase. The delta T is increasing, then it will increase the heat load. So for roof, like the values are very high because solar radiations will be very high on the roof. So that's why these data, this is very high. In the previous case, we have calculated the delta T between 35 and 4, which is 31 degrees Celsius. Then you need to add this 2K or 3K to the delta T. So that will be the final delta T. So there are three details you want to calculate the transmission load. One is U. U factor is available already in the tables. It will be established by the insulation panel suppliers. Then area calculation is very easy. Like you can calculate the area of a particular wall. Then delta T. Delta T is the temperature difference between outside temperature and inside cold storage temperature. You need to add the correction factor if the outside wall is exposed to radiations. Once you add, you will get a final delta T. With these three data, you can calculate the transmission load. So transmission load, like it's not a major load on a cold storage, but that also will contribute to some amount of the heat load. So this is how we do the calculation for transmission load. Okay, let me go to next slide. The next load in the cold storage is product load. This is a major load. So transmission load will contribute to only 5 to 10% of the cold storage load because we are using a puff panel. The puff panel will prevent the heat from entering. Maximum it will prevent, but some minor amount of heat will still enter. That's very low. But product load is the major load, which will decide the size of the refrigeration equipment. So product load can be classified into product exchange, cooling, freezing, cooling after freezing, respiration, and packaging. I'll explain each and everything in detail. So let us start with product exchange. So product exchange is the load which a product brings into the cold storage. So let us say like we are designing a cold storage where we are trying to store vegetables. So vegetables, the temperature which we want, like inside the cold storage is 4 degrees Celsius. So this data is available in STN book. What is the final storage temperature? Like there is a temperature called TS. If you see the formula, TS, the final storage temperature. The final storage temperature, like is the optimum temperature, like at which if you store the product, the shelf life will be more, like it will extend. Okay. Then like you have one more temperature, which is initial temperature. So when you bring the product will be at a higher temperature compared to what we want. Here, like for say for vegetables, The final storage temperature required is 4 degrees Celsius. The entry temperature will be at a higher level. It can be 20 or 25. Let us say it's at 25. So you have a difference in temperature of delta T of approximately 21 degrees Celsius. So the 21 degrees Celsius will contribute to heat addition to the cold storage. So that we are going to calculate in detail. The formula to calculate the final storage temperature is same, Q equal to mcp delta T. The formula which we use here, this is Q equal to mcp delta T. Q is the heat load. Heat load, like here in this case, whatever heat loads we calculate, that is with the unit kilowatt hour per day. It's per day, so the time is also a factor here. That's why 3600 is mentioned here. For one day, what is the heat load it is going to contribute? So that is what we are trying to calculate here. Then second, M is the product exchange. Per day, how much new product you are bringing and how much old product you are taking out. So product exchange kg per day. So it's kg per day. In one day, how much kg you are bringing inside the cold storage. This is M. Then CP is the specific heat of the product. So each and every product will have some specific heat. So the specific heat data is are also available in history and books. I'll show you a graph where like specific heat of each and every product, like majority of the products are covered here. Then as I said, T1 is the product entry temperature, TS is the final storage temperature. So with this data, you can calculate the uh, product exchange load. So this will give you the product exchange load. But in addition to the load, like when we are doing a refrigeration, like our cold storage design, we should make sure that the air circulation should be proper for all the products. So the product, like you can see, air like must be able to get around and in between the products. There should be proper air circulation. If we don't have a proper air circulation across the product area, the temperature like maintenance will not be same. You will have different temperatures at different areas of cold storage. So the temperature may not be same and there will be like damage of the products. So air circulation also should be proper. So if you have proper air circulation, then the load calculation process is this. So Q equal to mcp delta T. So Q is heat load, M is the mass product entering the cold storage per day, CP is specific heat, T1 is the initial temperature, uh, TS is the final temperature. So with this, we can calculate the product exchange temperature. So next load because of product is respiration heat load. So if you take material like say cold storage, if you take vegetables after harvest also, there will be some amount of photosynthesis or respiration which happens inside the product. Because of the respiration, there will be some heat addition to the cold storage. So all the products will be made up of sugar. The sugar, when it come in contact with oxygen, it will have a chemical reaction and it creates CO2 plus water vapor plus heat. This heat will be added to the cold storage. This we call it as respiration heat. So this respiration heat will be there only for vegetables and fruits, not for meat. Like it can be chicken or it can be fish. These like these materials will not respirate after harvest. Chicken or meat will not respirate. The respiration load for chicken or meat will be zero. So, but whereas if you store vegetables or fruits, there will be respiration because the sugar will come in contact with oxygen and it will create CO2 and water and heat. If you take any product, it can be any fruit or any vegetable. So generally what we do, we start cooling the product. So we will reach the freezing point. So whatever the heat the product is giving to cold storage during this process is called sensible heat. So this sensible heat will add a heat load to cold storage. Once it reaches freezing point, then so the water and other things inside the product will start to freeze. When it is freezing, it will emit latent heat. This is also a load to the cold storage. So after this latent heat is emitted, then like we will cool it below freezing point. Say like our freezing point of water is 0 degrees Celsius. If you are going less than 0, say minus 20. So from 0 to minus 20, again you will have some sensible heat. So there are two heats mentioned here, latent heat and sensible heat. The heat gain or loss because of change in temperature is called sensible heat. The heat gain or loss because of change in phase is called latent heat. When you start cooling from 25 to 0, so whatever heat you are observing, which we call it as sensible heat, then after it reaches 0, the liquid water will become ice. So this time there is a phase change between liquid to ice, liquid to solid. So this phase change, because of phase change, some amount of heat will be emitted, which we call it as latent heat of freezing. Then after all the water becomes ice, the temperature will drop. So like we are going to drop the temperature say to minus 20. So then minus 20, like 0 to minus 20. So what is the heat we are going to remove? So all these three heats will add together and it will create respiration heat. So how to calculate the respiration heat? So there are three formulas. You have to split the heat load into three. First, cooling before freezing, then freezing, then cooling after freezing. So all three will have three different formulas. So let us start with cooling before freezing. So cooling before freezing. So the formula is Q equal to mCp delta T. M is the mass of the product, like entering per day. Then Cp is the, so you will have two CPs, like Cp is the specific heat capacity. So if you take any product, it will have a specific heat capacity. But the specific heat capacity will be different at a different conditions. So above freezing point, you will have a different specific heat. Below freezing point, you will have a different specific heat. At the time of freezing, so it's not called specific heat, it's called latent heat. So there are three heats here. So specific heat above freezing, and specific heat below freezing, and latent heat of freezing. So these three heats are going to contribute, or like are going to add heat load to our cold storage. So first, to calculate the heat load before freezing, we need the specific heat above freezing point. So M is the mass flow rate, mass product mass which is entering the cold storage. T1 is the initial entry temperature, which will be some majority of the times equivalent to ambient. If a customer is cooling in a blast freezer and is bringing it, what is the temperature like of the blast freezer? That will be the initial entry temperature. Then till freezing point, like so, if your product is entering at 20 degrees Celsius, freezing point is 0. So 20 to 0, we call it as cooling before freezing. So the T2 will be 0, T1 will be 20. So this is the delta T. With this formula, you can calculate the cooling before freezing. Then once it reaches 0 degrees, the water present in the product will start to freeze. So at that time, the mass M remains same. L is the latent heat of freezing. So like heat emitted when there is a phase change. So the value is fixed, which is 335 kilojoules per kg. So humidity content of the product like multiplied by the humidity content of the product. So since we are going to only freeze the water, we are going to take only water load into the consideration. So you can see M is the mass of the total product. Total product means all the say like you are taking orange or like vegetable, say tomato you are bringing. So tomato total, say like you have 10 tons of tomato, all 10 ton is not water. So out of which how much is the moisture present? So in that how much energy we spend to freeze the moisture, that only we are going to take into consideration. So that's why we are going to consider humidity content of the product. So we like say 10 tons is there. The moisture content is 5%. So which is approximately 500 kgs. 500 kgs of water will be present in the 10 tons. In this 500 kgs, so we are going to multiply it with 335 kilojoules per kg. So 1 kg, to convert 1 kg of liquid to water, we need to remove 335 kilojoules per kilojoules of heat. So for 500 kgs, 500 into 335. If the moisture content is 10%, it is 1000 kg for 10 tons. So what we need to do? We need to take the product load, product mass. Then we need to consider the moisture content in the product. Then we have to multiply it with 335. So with this, we can calculate the latent heat of freezing, Q6. The next is Q7. So cooling after freezing. So cooling after freezing, the mass remains same. So initially we cooled from 20 to 0, then it stayed at 0. After all the water, like liquid becomes water becomes ice, then the temperature will start to drop. Till what temperature we are going to go? So T2 is the freezing temperature. T3 is the final temperature which we want in the cold storage. Say it is minus 20. That means 0 minus 20, which is 20 degree is the delta T. So M is the mass. Your CP. CP is the specific heat of the product below freezing point. So here, like we have majority of the data, we don't have two data, which is CP of the material above freezing point, CP of the material below freezing point. So how to get this value? So like, this is a table where generally I refer to take the data, but it's available in history and books. You can refer and you can take. If you see the table, you have all the products, like most of the products available, all the fruits. So in this table, there is a specific heat you can see here, like specific heat. If you can see my cursor, there is a specific heat above freezing, then specific heat below freezing, then latent heat of freezing. So specific heat above freezing for orange, it is 373.7 kilojoule per kg degree Celsius. Specific heat below freezing is 1.95 kilojoules per kg degree Celsius. Then latent heat of freezing is 290. So these three data are available here in this table. With these three data, you can calculate. So mass is already available. Then specific heat above freezing and below freezing and latent heat is available. Then the only thing we need is the delta T. What is the entry temperature? What is the freezing temperature? And then what is the final temperature? These three temperatures we have to decide. And moisture content percentage also is mentioned. If you don't know what is the moisture percentage, you can see here the moisture percentage of different products are mentioned here. This we can directly take and we can calculate the heat load calculations with this. So till now we have calculated the product load. In this product load, we have three. We will split it into three parts. First is heat load because of like heat load before freezing, heat load during freezing, heat load after freezing. All three how to calculate we have discussed. Now next is package load. Many of the fruits and vegetables will not will have some storage packages. It can be wooden package or it can be like cardboard box. So these packages also will come into cold storage. So this package material also will have some heat, so it will enter at a higher temperature. Even the package temperature has to reduce when we are keeping it inside the cold storage. The package material temperature also will reduce and it will reach the desired temperature what we are trying to maintain to the product. So the formula remains same to calculate the heat load of the package material, which is MCP delta T. M is the mass of the package. So what is the package material weight that we need actually? Then CP is the specific heat capacity of package material. If it is wood, wood has some specific heat. If it is cardboard, cardboard has some specific heat. These data are also available in a strand book, which we can take. T1 is the initial temperature, which is entry temperature. T2 is the final or storage temperature. So these two temperatures sometimes exit temperature. These two temperatures we have to calculate. So with this we can calculate the package load. Okay, so we have the package load and product load. These two things contributes to the uh, product load of the cold storage, which is a like considerable value in a total heat load actually. So transmission load will be 5 to 10%, but product load will be very much high. So this will decide the size of the machine. Then the next load is internal load. Internal load is because of different reasons. The first reason is people. Second is lighting. Then electrical equipment, machines, forklift or truck. So we use a forklift or truck to load or unload the materials. When a forklift is entering into the cold storage, it will generate some amount of heat. So that heat also has to be taken into consideration. If you see any electrical equipment, if you are installing a electrical bulb or like any electrical equipment, so that whatever electrical energy we supply to them, that will be emitted as heat. Those heat also we have to remove. So that also will be added to the heat load. Then light everything, each light, when we supply electricity to the light, it will bulb, it will convert the electricity into light energy. The light energy whatever we generate, that will be converted to heat at the end. So that will add to the heat load. Then people when they do work, so there will be two type of heats which is getting added. So let sensibility and latent heat. So the body heat will be transferred to the cold room. So that also has to be taken into consideration. So how to calculate each and everything, we will discuss in detail. So first let us see people. When people are entering the cold storage, people enter cold storage because of number of reasons. So to load and unload product, to check the inventory. So there are number of reasons people will enter. So when then they are entering, they will enter like their body or their dress, everything will be at a higher temperature compared to what we maintain inside the cold storage, which will be very low, 4 degree or minus 20. So because of this temperature difference, there will be a heat emission from the body of the person, and it will be absorbed by the cold storage. So cold storage will absorb the heat. This will add the heat load. So how to calculate the heat load for of a person? The Q equal to NTPH. This is the formula. If you see here. So what is N? N is number of people. Like how many number of people entering the cold storage? It can be two or can be four, depending on the requirement. Then T is the working time. That means hours per day. Say you have 10 people entering for 15 minutes a day. That means you can convert that into man hours. So 10 people into 15 minutes, which is approximately 150 minutes. 150 minutes, like you have to convert that to hour. So 60 minutes is approximately 1 hour. 150 minutes is 2.5 hours. So 2.5 hours, 2.5 is the T. The calculation is very simple. We need to convert the man hours. Say T is the working time in hours per day. Okay, if a person is working for 1 hour, like it's one actually. N into 2 we need to calculate in detail. Say N is the number of people, 10 people means 10. T is the working hour per day. If he's working only for 15 minutes, it's 0.25. If he's working for half an hour, it's 0.5. If he's working for 1 hour, then it's 1. So we need to calculate in detail. Then pH, heat release person. pH is heat release per person. So what is heat release per person? A person, like because of body metabolism and because of the temperature difference, there will be some heat emission from our body. How much heat it is emitting? So there is a value here. So if the cold storage is maintained at 10 degrees Celsius, the heat emitted is 210 watts. If it is at 0 degrees Celsius, the heat emitted by our human body is 270 watts. If it is minus 20, it's 390 watts. So the heat emission will increase by decrease in temperature. So because of a temperature gradient between our body and the cold storage, the heat will emit. The temperature gradient, if it keep on increasing, if you reduce the cold storage temperature from 10 to 0 to minus 20, the temperature gradient will increase. Because of the temperature gradient, the heat emitted by our body also will increase. So the formula is again like Q equal to N into T into pH. N is the number of people and T is working hours per day. Per person per day. If a person is working for half an hour, it's 0.5. If they are working for 2 hours, it's 2 per day. We need to take the value in per day. So with this, we can calculate the load because of people. Then next is internal load lighting. So okay, as I told you, in cold storage we need lighting so that we can access the materials very easily. But when we supply electricity to a electric bulb or electric illuminator, what it will do? It will convert the electricity into light energy. But this light energy will not go out. It will be inside the cold storage. Say we are supplying 100 watts to a bulb. 100 watts will totally become heat load. If you are supplying 150 watts or 200 watts or zero point 0.5 kilowatt, 500 watts. If you have 10 bulbs of 100 watts, which is 1 kilowatt, the total 1 kilowatt will be added to the heat load of the cold storage. So how to calculate it? It can be calculated in two ways. First option is area based. Second option is reactance based. If you see area based, so many of the times when we design the cold storage, we will not be knowing how many number of electrical bulbs the customer is going to install. If we don't know that value, so there is a thumb rule, like say per square feet this much light energy is required, like that. So if you know the thumb rule, you can do based on the thumb rule. If you see the formula here, Q is equal to A PVT by 1000. Q is the heat load, as I told you. A is the area is the warehouse storage area. P is the lighting load, I mean watt per square meter. So for every square meter of area, what is the lighting load you are going to give? So it's 1.5 watts per square meter. This is a standard we use. In some cases it will be higher, in some cases it will be low. The next is the T. T is the time lighting is used. If you take a air conditioning application, like the time this factor will not come because the load like lighting will be most of the times. In case of cold storage, how many hours you are going to use the light, so the time also is a factor. So these things we can use and to calculate the lighting load. So this is a area based. This option will be used if we don't know what is the exact amount of electricity we are supplying to the electrical bulb. But if we know the exact amount of electricity which we are supplying, we can directly include it into the heat load. So that option is called reactance based. So again, the formula is Q equal to P into T into F. Q is the heat load. P is the lighting load. Lighting load means how many, like what is the electricity we are giving to the light. Electricity, 100 watts or 50 watts. What is the electricity we are giving? T is the time, again, time used. Then F is the adjustment factor. Like say we have 10 bulbs or 20 bulbs, which is using 100 watts each. So 20 bulbs, 100 watts each is 2 kilowatt. So 2 kilowatt will be the P value. T is the time. Say like hours per day. We are going to use the light for 1 hour. So that means 1 is the value for T. And F is the adjustment factor. So adjustment factor we generally consider 1.25, like correction factor 1.25. So to have a better load, okay. So adjustment factor 1.25 you can see here. With this data, we can calculate the lighting load. Then the next internal load, which is very important, is electrical equipment. So if you see, there are number of electrical equipments which are used in the cold storage. It can be forklift, or it can be some kind of a motor, or it can be elevator, or vacuum machines. So whenever there is an electrical machine which is entering the cold storage, this machine will generate heat. So how to calculate it? So first, if you are using a motor, the total power supplied to the motor will be emitted as heat. The motor power has to be taken. Say like your 5 kilowatt motor, 5 kilowatt is your cold storage heat load. If you have 500 watts motor, 500 watts is your like cold storage. So whatever the energy we supply to the motor, everything has to be. If you have a fan, so whatever energy we supply to the motor, everything will be added to the heat load. That has to be added to the heat load. Its electrical kilowatt will become heat load kilowatt direct. There is no change in that. Then if you are using forklift, if it is electrical forklift, the electrical energy it is consuming, that will be the heat load. So one more formula is there. You can see the formula is Q equal to NPT. N is the number of devices. P is the heat load, which is kilowatt. T is the time. But then time is also a factor. How much time you are going to operate? Hours per day. N is the number of devices. Say we have 5 motors, which is zero point 0.5 kilowatt, which is, so 5 into 0.5 kilowatt, which is 2.5 kilowatt. Then P is the heat load. Then like so 5 motors are there, one forklift is there, and then like a vacuum machine is there. Each and every equipment you have to take, then you have to multiply the number of device, multiply it with the heat load, and then multiply with the time. So this will give you the heat load. This has to be calculated for each and every equipment. Motor separately we need to calculate. Vacuum machine we need to separately calculate. Then then forklift we need to separately calculate. So all those things has to be separately calculated. All the electrical equipments which are entering the cold storage will emit heat. So this has to be separately calculated. So then blower and fans. If you see in a cold storage, like we will use a evaporator. In the evaporator, you will have a blower or fan. See, this blower or fan also will consume electricity. The blower, what it will do, it will take the electricity and it will run the like it will increase the pressure of the air. When air pressure is increased, say air is like at a 1 bar pressure. The 1 bar pressure is atmospheric pressure. So this it will increase to a higher pressure. So because of the pressure, the air will start flowing across the cold storage. Once the pressure increases, so the heat, like the energy from the blower will be transferred to the air. Now air holding the energy, it will blow across the cold storage. When the pressure again becomes normal, whatever energy it is holding, it will be emitted as heat. So at the end, if you are like having a blower which is say like 2 kilowatt or 3 kilowatt, the entire electrical capacity of the blower will be added as a heat load to the cold storage. If you have blower like of 2 kilowatt or 3 kilowatt, that will be added as a heat load. You can see the formula here. The formula is Q equal to NPT. So N is the number of fans or number of blowers. P is the power consumption of each fan. So this data will be available in the operator catalog. So what is the power consumption of fan? T is the time, how many hours you are going to run. So if we have these two, three details, we can calculate the blower and fan load. So after calculating all the loads, like we have calculated transmission load, then we have calculated the product load, then we have calculated the internal load. I'll summarize transmission load. If you take the heat load because entering because of temperature difference between outside and inside, we call it as transmission load. It will enter through walls, roof, and floor. So this we have to calculate first, then product load. So product will enter at a higher temperature, so it will reach freezing point. Then we will cool it below freezing point. So this has to be separated into three: heat addition, like because of heat before freezing, freezing after freezing. All three heats has to be added. Then package load. Package material will enter at a higher temperature, which will be reduced to lower temperature. So because of which there will be heat addition. So that we have to take into consideration. Then we'll talk about internal loads. In internal load, we have people, lighting, electrical equipments, all those things will come into picture. So the internal loads has to be calculated. Once we calculate everything, then we have to decide a safety factor. Even though we do everything accurately, there will be some items which we may miss, or like which will create problem in the future. So that's why we have some safety factor, which will anyway ranges from 1.1 to 1.3, depends on the person. So you can consider anything like between 1.1 to 1.3. So this is a safety factor we will consider. So after you have safety factor, so whatever heat loads we calculated, Q1, Q2, Q3, like so transmission load, product load, internal load, electrical load, people load, all those things we have to add. So if you add everything, you will get the Q value. So Q is not the direct heat load. So once you have the Q value, then we need to decide the pull down time. Pull down time is the time taken for a cold storage to bring the temperature from initial temperature to final temperature. So let us take a chicken as an example. If you take chicken, so chicken will enter at a higher temperature, say 20, 25, 30. So let us consider 30 degrees Celsius, chicken is entering a cold storage. We have to reduce the temperature of chicken to minus 20. So from 30 to minus 20, 50 degrees Celsius difference we are going to reduce. So this we are going to do in cold storage. But the concept is how much time we are going to take to reduce it. How many hours we are going to take. This we call it as a pull down time. The pull down time will decide the equipment size. It will have a very big impact on the equipment size. The pull down time becomes half, the equipment size becomes two times. The pull down time is two times, the equipment size will become half. It's inversely proportional. If we increase the pull down time, the size of the refrigeration equipment will reduce. So how to decide the pull down time again? So this, like there are a number of options. What we generally follow, you can see here, cold storage which is 4 degrees Celsius and above. We can like so cold storage where like you are going to maintain a temperature of 4 or above. If it is a gravity coil, then we consider 12 to 16 hours per day. Forced drop evaporators. Gravity coils means there is no evaporation force, like there is no blower or something. If it is a forced drop evaporator, you will have a blower which will blow the air, so that will circulate the heat across the room. So forced evaporators we consider 14 to 16 hours. Gravity coils it's 12 to 16 hours. So this is the pull down time generally we consider. Cold rooms below 4 degrees Celsius with electrical defrosting, hot gas defrosting, there are two options. So with electrical defrosting, it's 14 to 18 hours per day. Hot gas defrosting, it's 16 to 20 hours per day. What is defrosting? So when you go below 4 degree, like cold rooms below 4 degrees Celsius, there is a chance the temperature may go below zero. When it is going below zero, on the evaporator coil, the water vapor present in the air, it will condense and it will freeze and it will form ice. When it's ice formed on the evaporator, so this ice will block the airflow, and like the heat transfer also will be affected. So to remove the ice, people use either electrical energy or hot gas. Hot gas is a compressor outlet gas to remove the ice from the coil. So this also will add some amount of load. So if you are using electrical defrost, the pull down time considered is 14 to 18 hours per day. If you are using hot gas, Then the pull down time, like generally we consider is 16 to 20 hours. Then next is frozen food storage. Frozen food storage is electrical defrosting. We consider 16 to 18 hours. Hot gas defrosting we consider 18 to 20 hours. So this is the pull down time we generally consider. If a customer specifically asks for a specific pull down time, that also we can take into consideration. Generally, if customer decides the pull down, like we can consider that. If he doesn't share that, we can design any one of which. So now we have all the data to calculate the cooling load. So to calculate cooling load, we need Q total. Q total is the summation of all the loads which we calculated, which is transmission, product, and internal loads. In internal load, we have people load, electrical load, and lighting load. All those things we have added. In transmission load, we have like walls and floor and ceiling, roof like load because transmission through that. Then if you take product load before freezing product load, and after freezing product load. So all the values will be added together, which will be Q total. So then K is the safety factor, which we discussed. After like doing this also, we consider some safety factor. The safety factor can vary from 1.1 to 1.3. We can consider anything like between this. Then final is TK. TK is the machine running hour or pull down time. So we discussed in the previous slide what is the pull down time we need to consider. So above 4 or below 4 and frozen temperatures for longer period of time, electrical defrost and like hot gas defrost. What is the number of hours we need to consider? We discussed. We have to decide the number of hours. So the Q total multiplied by K divided by totally divided by machine running hours. So this will give you us the kilowatt. What is the kilowatt of the machine which we need to use to maintain the cold storage? So this is how we calculate the cooling capacity of cold storage. So till now, like I've explained in detail how to calculate heat load calculations for a cold storage. But many of you will be like this, whatever formulas I told, it may be too technical. If you feel it's too difficult, like each and every time if you are doing a cold storage design, it's very difficult to like do everything. Some of the data are available in S3 handbook, some data you may have to get from internet. But even though you have all the data, each and every time if you have to do this manually, it will be time consuming process. But like the basics should be known to everyone. If you know the basics, you can use softwares easily. So the basics should be known to everyone. That's why we start from basics. So I explained how each and everything will impact a cold storage heat load. So how to reduce the heat load at a cold storage can be decided. Like you can use number of options with these basics. So till now, whatever I've explained, like this process we use to calculate the heat load manually, but we don't have to use manual process each and every time, because considering the time or like number of cold storages, so there are number of softwares available in the market. So one such software is, you can see here, like I'm from Danfoss, I'm presenting a software which is provided by Danfoss. So in Danfoss Cool Selector, we have an option of calculating cold storage heat loads. So whatever I told, everything can be done in 5 to 10 minutes. For one cold storage heat load calculation can be done in 5 minutes to 10 minutes time. So like what we need to do here is, if you see the screen, this is the screen which you will get in the software. So we need to input the parameters: the length of the cold storage, width of the cold storage, and the height of the cold storage. Then what is the temperature you are going to maintain inside the cold storage, and what is the RH you want, and what is the pull down time, and what is the type of goods you are going to use. It can be mixed product, or it can be fruits, or it can be meat. Then quantity per day, how much kg you are going to bring into the cold storage per day. Then after that, air exchange, ambient temperature you are going to mention, ambient RH you are going to mention. Then door opening, regular or like often, or like you are not going to open, that you are going to mention. Then puff panel thickness, then lighting load, fan load, then like defrost. So if you have all the details with you, if you mention all those things, it will directly calculate the cooling load. Many of the details are like already pre-programmed in this. If you don't know something, you can leave like the data which is available in software, you can consider. With this, you can calculate the heat load. So it may take hardly 5 to 10 minutes. If it is a complicated cold storage, it may take more than 10 minutes, like it may take half an hour or something. So it's very easy to calculate. There are a number of softwares available in the market. So we use from like I'm from Danfoss, we use a software provided by Danfoss. It's available in our cool selector. Okay, so this is about heat load calculation. Then I have a refrigeration circuit, so which is used like after calculating heat load, we have to Select a refrigeration equipment which have to maintain the temperature at a proper level. This is a refrigeration component, refrigeration cycle, or like refrigeration components, what and all we use in cold storage. It's mentioned here. So we use a compressor, then we use a condenser coil, then we use a expansion valve, thermostatic expansion valve or electronic expansion valve, then a operator coil. So solenoid valves will be used, side glass, filter dryer, ball valve, pressure switch, pressure regulator valves, then oil separator. So all those components are manufactured by Danfoss. So we supply these components from Danfoss. So this is all about cold storage heat load calculations. If you have any doubt or like anything, you can reach out to us. So we will be very happy to answer all your questions. So thank you.
Thank you very much, Parthiban. This is a fabulous training program that you had. A lot of knowledge sharing, because typically in our industry, everyone is talking about heat load based on air conditioning, and putting in a cold room heat load calculation and the differentiation was absolutely brilliant. So thank you
Thank you,
very
sir.
much. Thank you very much for taking time out and sharing this information. And your training is going to be there on our platform for literally forever. So I'm sure there'll be thousands of people who will see this again and again and who will learn from this. So thank you very much. Thank you very much for taking time out and sharing this information.
So thank you for giving me opportunity to present. So maybe like our knowledge here. So 100%. Like if there is any question or anything like a customer or like like end user wants to know, or like they can reach out to us anytime. It can be me or
Sure.
like anyone from Danfoss. Like we are very happy to answer.
Sure. Thank you very
Thank you.
much. Thanks a lot. Thank you very much. We look forward to future sections from your side.
Thank you, sir. Bye.
Thank you. Thanks.
From the land that celebrates innovation and breathes enterprise, comes the next chapter of India's HVI Kantar journey. 3 cities, 4 milestones, 1 vision. RATA Conclave, India's most powerful platform for HVAC and our entrepreneurs, thinkers and changemakers. And now in 2026, we converge in Ahmedabad, the growth capital of the West, where business meets purpose and sustainability meets scale, empowering HVAC and our business for sustainable growth. 1,000 plus delegates, 70 plus industry speakers, 80 plus partners, 3 power-packed forums, national MSME awards, live networking and product showcases, a marketplace of ideas where innovation scales, connections deepen, and opportunities compound. Experience it all in the soul of Gujarat, culture, cuisine, and celebration. Only in Ahmedabad. Join the movement for MSAMS to thrive, manufacturers to evolve, and the ecosystem to advance. Mark your calendars, 25 and 26 September 2026.